Good morning, my fantastic superhumans. Thank you for coming along. I acknowledge the traditional owners of this land. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. Now, I am not really on the top of my game right now, so let's see how this goes. And the other thing is that my computer is being really laggy again, which is not good. Yeah, voice and video out of sync. My computer was doing a backup this morning right when I started opening everything up, and I've cancelled the backup, but it's in the process of doing its cleanup. It doesn't end instantly, so hopefully in the next minute or two it will catch up with all its disk I/O and alright, looks like it might have just finished. So hopefully OBS will get itself back in sync and we'll be happy again. Alright, the important thing is people can hear me okay? I think so. Alright, so I've got a couple of random, well not so random things to cover today. I'm going to try not to forget anything. I've got some notes for myself, so hopefully I will cover it all. Now the first thing I should mention is Patreon discount codes. So I got a message from a patron just a day or two ago saying that the discount code doesn't work, and that is because it rolled over into July and I hadn't posted a new code. So I'm sorry about that. I will take care of it after the live stream. I'll create the new code and mail it out to patrons and to GitHub sponsors. It seems that every single time the code expires, it catches me unawares. I'm really sorry about that. So the next thing is that there is there's going to be a live stream. Sorry, I'm mentally reviewing the different things I've got to cover. So the Maker stream is going to be on. So for those of you who don't know, the Maker stream is a regular live stream, which is done sort of like as a group live stream, and it's hosted on a different channel each month. There is a group of makers who sort of rotate around among themselves, and there are usually between 4 and 6 people on the live stream. And I'm going to be on the next live stream, which is going to be starting I think in about 18 hours. So it's in the very early hours of Monday morning for me. And I will drop in a URL. So I'll try to remember to do this at the end of this live stream as well. So don't click on this just yet, because you'll go away from here and go over to the other one. But that is going to be the URL for the MakerCast live stream. And so I'll be on that with David Watts, Clem Mayer, who you may know as Mayer Makes. It's got a good YouTube channel. Dave Darko, James Sharman is going to be on there, and Bit Looney. So it'll be interesting to see what sort of projects they've been working on recently. Yes, on David Watts' channel. So David Watts is hosting at 10 PM CET. Great. So that's 2 of my housekeeping notes covered so far. Also, another really cool suggestion that came from Discord member Cable Tie. He contacted me about a week ago with a suggestion that I do design reviews on the live stream. And I think that's a really cool idea. So it needs to be done in a careful way, of course. So, sorry, to back up to explain the idea. The general principle is someone has been working on a design for a board or a project or whatever, and they want to get some feedback on it and suggestions. It could be prior to going to production for a PCB, so during the design process. In a company where you have other people that you're working with, it's fairly common to do a design review where you'll take your design and go through it with someone else, and they can be an objective pair of eyes that looks at what you've done and comes up with suggestions for improvements. And the idea is that it's not a case of picking holes in things and being critical. The idea is that it should be a way of catching mistakes before it goes to production and coming up with suggestions for improvements and basically just making the design better. So you can think of it as being like an editorial review, or as a writer, you put something together and it goes to an editor who goes over it and makes sure that everything is polished and ready to go to print. So the idea is that people could submit a design, which could be something like the design files for a circuit board, and then I can go over them on the live stream and provide some feedback. And part of the value of that, well, it's valuable in several ways. It's valuable to the person who has done the design because they get a third person, like a third party perspective on what they've done and maybe some ideas about things to improve. By doing it on a public live stream, it's probably very nerve-wracking for the person that has done the original design because it's being held up for everybody to see and discuss. But it's also valuable for other people to see that because it can help with the process of how do you look at a design and figure out ways that it can be improved. So doing a design review in public could be a really useful thing. So I'm probably going to do that. And I've done many many walkthroughs of my own projects over the years. I've spent many hours on live streams showing things in Eagle. In fact, I'm going to do that in a moment with something I'm working on right now. And so the important thing is that I want to make sure that if I do this, it's got to be done in a positive and respectful way. It's not an opportunity to point at someone's design and say, haha, you did this wrong, or I found a mistake. It's about trying to see, well, it's partly finding the good things that people have done as well. One of the really cool things about looking at designs is you see solutions to things, and the more designs you're exposed to, the better you become yourself at recognizing good and bad practices. So I'm going to James, yes, you're sure that I will be a lot kinder than Dave Jones? Yeah, Dave wouldn't hold back. Yeah, I've seen him do design reviews before, and it's he can be very direct and harsh. That's just not my nature. So, if anyone has a project that they would like to have a design review done for it on a live stream, please let me know. Maybe in Discord. And on that subject, I've just created a new channel in Discord. It's in where? Which section is it? I can't even remember. I just created it a few minutes ago. It is in the Tools and Techniques section. There is already a channel called Board Design, which is where people can discuss projects they are working on. I've just created a channel called Design Review, which is really for this purpose. And I think those two channels have slightly different purposes. That's the reason there are two of them. So board design is more for things like, I'm working on a particular project and I've got this problem and how do I solve this? It's more for quite specific discussion. Whereas design review is a case of, here are my design files and I would like feedback on this design before I go to production. So please check it over and see what you can find. And perhaps that's a good place to begin with finding some designs that we can review on the live stream. So if you've got a project that you want to put up for design review, please post in the design review channel. And if you're okay with that being done on the live stream, let me know and we'll do it here. So following on directly from that, let's have a quick look at something I've just been working on. But first I'm going to get myself set up. So I've got, let me see, well, I'll switch to the desktop view. Oh goody, my turn that off, turn that on, turn that off. Okay, so I'm going to grab that and drag that across to there so that we can see more of what's going on. Alright, so this is the Ether 10, the current design. So it's the Ether 10 version 3.0, I think. Jacob asked, said, I have a rough PCB I've been playing with for my 64 channel digital input, 192 channel PWM output, RGB LED button controller. Too detailed for live, or send it? I think that sounds good. Maybe if the design files are up somewhere that I could access them, like on GitHub, then maybe just drop the URL in that design review channel in Discord, and I'll have a look at them. But yeah, that sounds like a really good candidate. Alright, so I'm losing myself already. How can I have lost the train 12 minutes into this? That's ridiculous. Alright, so this is the Ether 10 version 3. And I'm just pulling this up as a reference for where I'm coming from with the EtherUno design. So, alright, so the Ether 10 design, the original Ether 10 design, is 10-ish years old, and the very first version, well in fact all of them up until now, have a WIZnet W5100 Ethernet chip on it. The reason that chip was chosen, at the time, there were really two solutions to adding Ethernet onto some kind of an Arduino or microcontroller project. They were the ENC28J60 and the W5100, which was, and I'm not sure if there were other siblings for it. I think there was an earlier version like the WIZnet 4400. I can't even remember. It's like a decade ago. But there were really only those two chips that were in common use for Arduino and microcontroller related projects. The original official Arduino Ethernet shield had a WIZnet W5100 on it, and that was actually the reason that the chip was chosen. Well, there were that and the fact that the drivers for the ENC28J60 are absolutely horrible. I did a little bit of work on the drivers for the ENC a long time ago, and the way the drivers were written was just really painful. It was very hard to work with. And the WIZnet drivers were much nicer. And more importantly, the WIZnet drivers were included in the Ethernet library, which was shipped by Arduino, by the Arduino team as part of the IDE, which meant that if anyone installed the Arduino IDE, they automatically had support for the WIZnet. And that's why we ended up using it. So both the Ether Mega the Ether 10, and the EtherUno all had the WIZnet W5100 on them. Now, the thing is that the W5100, as I understand it, I might be slightly wrong here, but I think the way that chip came about is that it was based on off-the-shelf silicon. It was an existing microcontroller core that was customized to turn it into an Ethernet controller chip. And it was not particularly efficient. So one of the things that the 5100s are notorious for is running really, really hot. It would be normal for those chips to be running at 80 degrees. I'm talking about Celsius here. So I don't know what that accounts to in Fahrenheit, but it's hot enough that the entire board gets really noticeably hot. And if you touch the top of the chip, it's close enough, like it won't burn you, but it will make you go, oh crap, and pull your hand away in a hurry, because it's hot enough that it is really painful to touch. And so I would regularly get customers who would say, my board is running really hot, there's something wrong with it. And I'd have to say, no, sorry, that's normal for the 5100. The specs and the data sheet say that that's normal. It's just the way it is. But not really ideal, particularly for a board that might end up going inside an enclosure or in an enclosed space. So the Ether 10 was really a derivation of the Freetronics Ethernet Shield design. It was the Freetronics Ethernet Shield and the Freetronics 2010, which was like an Arduino, well, it predated the Uno, but it's kind of like an Uno equivalent, smushed together onto a single board. If you look at the schematic of the Arduino 2009, which is the board that came out before the Uno, and the Ethernet Shield, and you just jam those two schematics together, that is essentially the schematic of the Ether 10. So it's functionally equivalent to those two things stuck together on a single PCB. And that's what you see in front of you right now. Although this is after a couple of iterations. It's also got power over Ethernet support and that sort of thing. So over the years, WIZnet have released a number of successor chips to the 5100, and there was the 5200, it's 5500, they've now got the 6100, and they've been improved in some significant ways. The 5100 now is old enough that you can still buy it, but it's not easy to buy. In fact, the cost of manufacturing of the Ether 10 has gone up. So this board costs me more to make now than it did 10 years ago, because the cost of the W5100s has risen due to poor availability. They are still being manufactured because there are existing designs that they need to service. But yeah, that chip costs more now than a modern chip, which is faster, has more memory, can support IPv6 and can support more simultaneous sockets, and runs cooler and is smaller on the board. So there, other than it already being built into the design, there is absolutely no reason to use a W5100 in a new design today, unless you wanted absolute 100% compatibility with the original Arduino Ethernet library. So a project that I've been undertaking for a little while now is redesigning this. Now the other thing is, if you look at the schematic, you will notice something. Now this board was designed in Eagle, like the original, as I said, was 10 years ago. When was this revision? So this revision, well, even this one, so this is version 3.0. This is the design that is shipping right now today, was updated in 2013. That's how old it is. It's nearly 7 years old. Nearly 7 years since the last revision. And at the time, the limitation on Eagle licenses meant that for the hobbyist version, you could not have multiple sheets in your schematic. That was one of the ways they restricted it. So there was a limit on the board dimensions, the number of layers, and you could only have one schematic, and that was the hobbyist limitation. So this design was done across multiple pages, all jammed onto the same schematic sheet. Each of these frames that you see is a single A4 page. So this was essentially a 3-page design, if you account for the mostly blank page, which had the prototyping area and the headers on it. And this was laid out in this way so that if you hit print and you have your paper size set to A4 with 100% scaling, you will get 3 pages coming out. And the print driver splits this up and does it as 3 separate pages, which is kind of convenient. But doing it as one sheet like this with 3 pages all jammed together is not ideal. So, and the other thing is that you can see that it's just very hard to follow. The whole schematic is jammed in fairly tightly, and there are some really horrible things, like you can see these ground symbols coming off sideways, which you do see in a lot of designs, but I just really don't like it. Even worse, look at this one. There are ground symbols upside down here. That is horrible. I don't like that. And also there are some other changes, like the way the labels are done on these nets. That's kind of, that was just done that way because that's how Eagle worked back in those days. So it was all due for a change. And you can see that what I tried to do here was break things up into logical blocks. So I put some big dashed lines around sections of the schematic and put little headings in there. And you can see, you know, the auto switch here, where it selects between either the USB power source or the DC input coming from the 2.1mm DC socket. So it's kind of everything smushed together into this schematic, which is kind of painful. So one thing I've been doing over the last couple of weeks, off and on in between other things, is looking at redoing this. And where I'm up to at the moment is this. This is still a work in progress, but I'm getting there. So what I've done is split this up into a number of sheets. So if you have a look down the left here, oh, that scaling is pretty crappy, but anyway, that looks alright. So we've got 4 separate sheets now instead of 3 virtual sheets on a single sheet. We've still got the one down at the end, which is an area where you can draw your own project and indicate how you're hooking up to the I/O pins. And then this one is the first sheet, which is the 2 microcontrollers and the ICSP headers. Now, one thing that I'm not really sure about in terms of how I should organize this is which sheets to put first. Because ultimately, I suppose it doesn't really matter, but I've tried to group things in a logical way. So the first sheet is the primary microcontroller, its ICSP header, and the USB to serial adapter and its ICSP header. So this is the core of the brain of the board. And down here in the bottom, you can see the ATmega 328P microcontroller. So this is the primary microcontroller, which is doing all the work of running your sketch or your program. And you can see I've switched the labeling style here. So I've got labels hanging off the ends of these nets instead of the label sitting above it. You can see up here where it's got reset. Let me select that. So the reset label is the other style where the label sits on top of the net, and then these ones have got the style with the thing that's like a little ribbon hanging off the side. So this, and you can see here the link between the yeah, so there's the link. Oops, what am I doing? Wrong tool selected. So there's the serial link between the USB to serial converter. So the connection comes in here. Oh, and also I've switched over to USB-C. So this is a USB-C connector, but it's an interesting connector. You'll see this on the footprint in just a moment. Most USB-C connectors are horrible to work with because the footprint on them is really super tight. And the most common ones have a combination of some surface mount pads and some through-hole pins, and the through-hole pins are tiny. So you need like 0.3mm holes for the pins, 0.3, 0.4, something like that. Anyway, it's small enough that board fabs look at it and go, what are you doing? And because USB-C connectors are backwards compatible with the older, slower USB-C, USB standard, like USB 2.1, etc., what you can do is use the USB-C connector for the older style USB, but then you don't need all of the extra pins. And the really horrible footprint that you have to deal with is just a pain when you're laying out a board. So what a couple of manufacturers have done is made a version of a USB-C connector that only has the pins that are necessary for regular USB 2 point whatever it is, and it doesn't have all of the extra pins, which means that the footprint is a whole lot nicer to deal with, and the connectors are simpler. So what you can see here is the connector that only has a few pins coming out of it. Now some of these pins actually represent multiple pins. Like VBus, for example, is on a couple of pins. Ground is on a couple of pins. D plus and D minus, because the connector is interchangeable, are on 2 pins each. So there are more than you see here. You can probably hear that. The dog next door going insane. I hope it's okay. That dog does tend to go nuts a lot. I think it's very bored. It just sits at home and barks. So, yeah, so what we've got here looks very simple for a USB-C connector, but it gives us everything we need to still be able to do a regular connection. And you can see it's got a couple of 5K1 pull downs on here. So I've got a pull down resistor on each of the CC lines. And I can't remember what CC stands for. I think it's charge current or charge control or something like that. Those are the pins that signify to the other device what the power capabilities are for our device. And if you put a 5.1K resistor on the CC pins and pull it to ground through a 5K 1% resistor, the other device, if it's like a device that supplies power, will see this as being an old style USB device that can take 5 volts, 500 milliamps. Because the new USB standard allows for higher voltages and higher power. It's got things like the PD, or the power delivery standard, which is used for things like running soldering irons off USB or charging laptops. You know, those sorts of things where you want a whole lot more power than 5 volts, 500 milliamps. And you don't want to plug your little microcontroller board into into some device that can supply a whole lot of power and suddenly have 19 volts shoved down the supply line, because we only want 5. 19 volts would not be very healthy. So those two resistors set the mode, and they tell whatever is supplying power to this device that we only want 5 volts at up to 500 milliamps. And there's a polyfuse in there. Anyway, I'm going into more detail with this than I expected to. I thought I would just be talking about this for 30 seconds, but oh well, maybe it's interesting. Alright, so from USB So we've got the connection from USB coming in here. It goes into the ATmega 16U2, which is in itself a complete functional microcontroller. It just happens to be used as a USB to serial converter in this case because it's got firmware loaded on it that does that job. So for many projects, what you would use is something like an FTDI USB to serial converter or a Scilabs chip, like or maybe a CP2102N, like I've used on the new ESP flasher board, which I'll get back to. I haven't forgotten about that. I've got a few of them right here. So in this particular job, and if you use something like a Wemos D1 Mini, they typically have a CH340G USB to serial converter, which is a horrible chip, but it's used because it's the cheapest that you can possibly get. Now, this was an interesting and unexpected design decision by the Arduino team when they brought out the Uno, and previous boards like the Arduino 10.000 and the 2009 used FTDI USB to serial converters on there. And in fact, that's what we did on the Freetronics 2010. So the 2010 was the board that came out in 2010, hence the name, and it was based on the 2009. So yeah, if you look at the early Arduino boards, they didn't have that 16U2 on there. They had an FTDI USB to serial chip. And there seem to have been two motivations for the replacement of that chip. And the reason that the 16U2 is used right up to this day on official Arduino boards, even though it's more expensive than a dedicated USB to serial chip. One reason was philosophical. It was the idea that the USB to serial chip was a bit of closed silicon that was beyond your control. Now, I'm not quite sure how I feel about this justification. This seems strange to me. So, so in electronics design, we're used to treating silicon as black boxes most of the time. It's rare that you, unless there's something like a silicon bug or some weird behavior, it's rare that you really care how the chip itself is implemented. It's a black box with inputs and outputs and power rails and those sorts of things. But you don't need to know how the chip has been designed as long as it does its job and it behaves the way that you expect it to. And there is a big move at the moment towards open source silicon, designs of chips that have been published so that you can understand how the chip itself works and it's not just a black box. And that in itself is cool. But the idea of replacing a USB to serial converter chip only because it's a black box and you want something that you have more control over just seems like a very thin justification. Now with using the 16U2 on here and with the firmware on it, so the firmware that runs on it is all open source and you can see how it's doing its USB to serial conversion. So you can inspect it, you can fix bugs in it, all of the good stuff that goes with being open source. But for most situations, it doesn't matter whether you can inspect the internals of the USB to serial converter. Most of the time you don't care. It just takes USB on one side, it gives you serial on the other. How it implements that, you couldn't care less. So yeah, when the Uno came out, this was one of the justifications that the Arduino team kept talking about, saying they wanted to come up with a totally open source solution and they and it was part of the philosophy of Arduino being open source. So, I don't know, that's fine. As everyone here knows, I'm a big proponent of open source. I really like to see designs released so that they can be inspected, but it seems like a bit of a thin justification for that design decision. Alright, so the second justification, and this is where it actually makes sense, and I think this is a worthwhile thing, is a technical justification, which is that if you use a 16U2 so that you can reprogram it, it means that you can make your board behave in a different way, and you can use it for doing things like HID emulation, which means that your board can pretend to be a mouse or a keyboard or some other human interface device. And it does that by running code on the USB to serial converter that, instead of being a USB to serial converter, it does something else. And so this is really commonly done these days with the Leonardo. But the thing is that the Leonardo wasn't out when the Uno came out. The Uno was released, and some of the early example projects for it involved reflashing the 16U2 using its ICSP programmer to make it behave as a gateway between being a human interface device and the main program that was running on the main processor on the board. Now, this was a bit of a, I think this was largely lost on people, and it didn't really take off. It wasn't used very much. There were a couple of projects that did it, but it wasn't until the Leonardo came along that it became really practical to do this. And the reason is that if you reflash the USB to serial converter, so the 16U2, and you put some HID emulation gateway or bridge code on it, you can no longer flash the main processor unless you use an ICSP programmer. So the expectation was that what people would do is write two lots of code. One bit of code would be the HID emulation bridge that would run on the USB to serial converter chip, the 16U2, and the other would be the main project code that would run on the main processor. And then you've got to compile two lots of code. You've got to flash it onto the two microcontrollers on your board, and once you have replaced the code on the USB to serial converter, you can't use it for USB uploads anymore. It just doesn't work. So you can't go into the Arduino IDE and select upload. It'll fail. You need an ICSP programmer to load the code into the target processor. And this all worked. It's fine from a technical point of view, but it was just too much of a barrier for people to use this as a practical solution to building devices that would act as like a virtual mouse or whatever device you wanted to emulate. And so what happened was that it was fairly quickly realized that if you had an ATmega 16U2 and you could do HID emulation on that, then what you could do is use a bigger processor with the same architecture. So on the Leonardo, it's an ATmega 32U4, and then you don't need the second processor. You don't need the main processor. Your interface device can do both HID emulation and run your program, and with the bootloader set up the correct way, you could still do USB upload. And that's essentially what the Leonardo is. So the Arduino Leonardo is like, if you look at an Arduino Uno, and then you cut off most of the PCB, and you leave just the USB to serial converter and the power supply, and then you upgrade the USB to serial converter chip to have more memory, because the 16U2 and the 32U4 are architecturally the same chip. The actual core that does the processing, it's basically the same thing. The same code will run on it. The difference is how much memory it's got. So it's more flash and more RAM on the 32U4 than on the 16U2. That's actually what the 16 and the 32 and the 2 and the 4 signify, is how much memory the chip has. But apart from that, it's the same chip. So an Arduino Leonardo is just the USB to serial converter component of an Uno board, with most of the rest of the board removed. Well, the rest of the circuit anyway. And what that means is that projects that originally would be done on an Uno with separate code running on those two processors can now be achieved with one lot of code running on a single processor. That makes the board cheaper to produce, but most importantly, it dramatically simplifies the job of writing the code to run on it, because you don't have to maintain two sets of code and upload using an ICSP programmer. You can just flash through the USB port. Anyway, this has been quite a detour from my original concept. Maybe it's useful for people, I don't know. I can talk about this sort of stuff all day. So, on this particular board, we still have the 16U2. Now, this is an area where I would actually be really interested to get some feedback from people, because with boards like the Leonardo and all of the many compatible boards, there really is no reason anymore on an Uno to have the secondary processor for the USB to serial conversion. This whole chunk of circuit that you can see right here, with all of this complication, so it's got an external crystal because it needs accurate timing. It can't run on the internal oscillator, and well, I don't suppose it's that much complication, but we do have an ICSP header specifically for the secondary processor. So what I could do in this design is just delete the ATmega 16U2 and put some other chip in its place, like a CP2102N. I mean, I could use an FTDI chip or something, like go really old school, but I'm using the 2102N on the ESP Flasher project, and it kind of makes sense to standardize on the same thing. Now, what that would mean is that it wouldn't identify itself in terms of the USB VID and PID in the same way, although that could be done through that could be done just by changing the values on the in the CP2102N. So all these years I have stuck to producing boards with a 16U2 on it as a USB to serial converter, kind of out of what's the term? I don't know. Habit, I suppose, but also to not stray from the upstream Arduino design. In the case of the Ether 10 and now the EtherUno, the idea is that it should be very easy to explain, and it should be 100% software compatible, because if you do take an Arduino Uno and an Ethernet shield, you join them together, what you have electrically is exactly the same thing as what I've got here as a single PCB. So there should be 100% compatibility. That's been the goal. And that makes it really easy to explain to people. It means that all of the examples work, the example code works. You don't have to explain to people why things are different, like you need a different USB to serial driver for this board compared to the official Uno board because it's got a different USB to serial converter on it. I just wanted it to be exactly the same. So zero friction using this compared to using the two boards joined together. Okay, so there was a comment from Station 240 who said, you see how the NoCan board's Omslow cells are set up, uses an STM32F042 as the CAN controller and programmer. It could also be USB driven. No, I haven't. That's that's definitely worth checking out. Thanks for that pointer. I'm going to have a look at those Omslow boards. No can. Interesting. I'm really into CAN bus these days, so I'm very interested in seeing boards that do that sort of thing. Now, as you'll see in just a second when we look at this PCB, this board is mostly laid out, and this area around the 16U2, I can't remember if I finished routing it or not because it's changed with the USB connector changing. I'll have to check it out. Well, we're about to find out. But I don't know, in my head I'm flip-flopping between leave it as is, we'll keep using the 16U2 and it will be exactly the same as it has been for the last decade, and there'll be no issues with compatibility, or switch this out for something like a CP2102 and potentially get higher throughput on it, like higher data rates. We get the benefit that we no longer have to flash the secondary processor, because one of the things you have to keep in mind is that when these boards are assembled at the factory, so at the PCBA, they then have to go through a process where the firmware is loaded onto them. So the bootloader has to be installed using an ICSP programmer, and the bootloader has to be installed on both the 16U2 and the 328, and the test programs have got to be flashed on them. So what we do is we have a test routine where it loads a test program onto the processors, and then it exercises the USB connection, and it exercises all of the I/O on the main, connected to the main processor, and it tries to find anywhere that the board fails. So any I/O pins that don't work properly, like the connection from the header to the processor is not correct, or short circuits or whatever. So part of that process currently is that we have to load the custom firmware onto the ATmega 16U2 as part of that commissioning process. And if I switched over to a CP2102N, I think the chip itself would be cheaper. It would probably save, I would have to look at the supplier costs and the bill of materials, but we could potentially save a couple of dollars on that part, because the cost of the 16U2 is probably significantly more than the cost of a 2102N, and we no longer have to do the flashing portion for that processor, which would save time in production, and we'd get rid of the ICSP header for it. I'm kind of inclined to go down that track. That will mean more rework of the PCB. I've got to make some more modifications to it, but it's going to save money, both on the bill of materials. It's going to save time in production. I think it's probably worth it. I would love to hear feedback on that. Does anyone out there care that the Arduino Uno has a 16U2 as the USB to serial converter? Have you done any projects where that matters to you? Or do you just go for something like a Leonardo compatible board, or like one of the SAMD boards that can do HID emulation when you're doing those sorts of projects? Because I'm inclined to drop it. I might delete that part and switch it out. For a CP2102N. So that passes the serial connection. So after this chip has done its conversion, it passes the serial connection through to the main processor, and there's nothing special to see here. It's just some reset circuitry. There's the crystal, its I/O headers. Because we're using the surface mount version of the ATmega 328 here, we get 2 extra ADC inputs. So we've got ADC6 and ADC7. Those are not exposed on the Arduino headers. It only goes A0 to A5, and that is because on the original Arduino, which I really should say Arduino, they had the DIP version of the ATmega 168. Yeah, it was the ATmega 168, and because of the limitations of the number of pins on the DIP format package for that, they didn't have enough room to put in to expose ADC6 and ADC7. So even though those analog inputs are in the core of the processor, there were no pins to put them on, and because there were no pins in the DIP format header, the Arduino team didn't design it onto the Arduino headers, and they just don't exist on a standard Arduino board. But those analog to digital converters actually do exist inside the processor, and they can be exposed. So on the other format, so we've got a TQFP32 is the format of the processor that we use on this board. Those extra pins are brought out because there are enough pins in the package to allow for it. So A6 and A7 are brought out here as little as extra headers, but they're just basically solder holes through the PCB like pads. They're not on the Arduino headers. Then what have we got? More I/O. Oh yeah, so here's one difference, and this is something that maybe I need to move these around a little bit to remove that annoying overlap. If I move these out of the way just to make it neater, you can see that PB5, so this is D13. In fact, I should stick a label on that. Let's stick a label right there, just for now. So D13. On a standard Arduino, if you run the blink example, there is typically an LED on the PCB that you can blink, and on a standard Uno, it's D13. So you can do digital write D13, high and low, and it will make the LED flash on and off. Now, on a standard Arduino board, like an official Arduino board, D13 is connected to an LED and a resistor to ground. That has a non-infinite resistance. So it's actually biasing D13 low by default, and it's biasing it low harder than the internal pull-ups can overcome, which means that if you are using D13 on an original Arduino and you want to use input pull-ups and say a button so that you can press the button and then detect when it goes low, you can't do that because the pin is already biased low through the LED, which sucks. It's I mean, I understand why it's done, but it just seems like it's because there are very limited number of I/O pins on a standard Arduino. It's a shame to lose a potential input, and you can still use it as an input if you are driving it hard enough. So if you've got, if you set it into input mode, and then you've got something that pulls it hard to 5 volts, for example, it'll still see it as a logic high on the input, and the LED will come on. So that's kind of a cool thing. So if you drive the LED high on a standard Uno, so if you drive D13 high from the outside, it'll turn the LED on and gives you visual indication. But you can't have it pulled high using the input pull-ups, and the input pull-ups on an ATmega I think are somewhere in the order of 22k ohms, like the internal resistors that are inside the processor itself. They may even be weaker than that. They might even be a higher value, which means that if you turn on the input pull-up on D13, it's never going to see a high value. It'll only ever see that input as low because the resistor pulls it low. Anyway, what we did here was decouple the resistor from D13 using a transistor. So there's a little MOSFET here, and what we've got is D13. In fact, what would have been neater? Let me change this labeling. I'll make this, yeah, there are better ways to do this, but that is probably slightly more accurate, even though it's ugly. I need to move this part of the schematic around a little bit, give it a bit more space. There's more room. I can move things now because I'm no longer being cramped in. I can move this whole part of the schematic a little bit to the left and make more room for myself down here. So D13, if you drive it high, will turn on this FET, which will allow power to flow through the LED, and the LED will turn on. And if you turn off the FET, there's no current flowing, so the LED turns off. So you can still blink the LED using D13. It works, it's functionally exactly the same as before. But the addition of this MOSFET means that you can now use D13 as a digital input, and the input pull-ups will work. So that's, I think, a worthwhile little change. So that's just a minor improvement over the Uno reference design. So D13 on the Ether 10, and also we did this also on the Freetronics 11. The 2010 did it, the 11 does it, the Ether Mega does it. Like, all the boards do it. And it just means that D13 is no longer a special purpose pin that has that limitation of the LED biasing at low. What else? Okay, nothing much else to show on here except that we've got the two ICSP headers, and they take up a fair bit of footprint. So just checking a couple of comments here. So Johnny Bergdahl said I would swap it, the 16U2, for a serial chip. It is 2020 after all. Yeah, that. And he also says HID board with Ethernet makes no sense to me whatsoever. Now, there are actually situations where that can be useful, but you're right that it is a very niche sort of application. Why would you have a board with Ethernet on it that also needs to emulate an input device to a computer? Now, there are interesting applications for that in terms of assistive technology, building devices that will interface or control computers based on signals from other places, like MQTT messages. So the idea is to be able to do something like publish something to MQTT and then have that output a message on the key, like a virtual keyboard, or move a mouse or a cursor or something. So there are use cases for it, but you're absolutely right that it's very niche. And the idea of, I was going to say compromising the design, but the idea of dictating the design choice to use the 16U2 and do HID emulation on it versus simplifying the design using a dedicated USB to serial chip just for that one little niche use case, yeah, I don't think that makes sense. And James asked, have you considered doing 2 alternate board loadings to offer full compatibility for extra dollars? No, I hadn't really thought about that, and I think it might be a little bit too much overhead. Running, what that would mean essentially is having 2 parallel designs with one relatively minor difference in them, and the burden for me of trying to maintain those 2 designs in parallel, and more importantly trying to maintain the stock level in parallel, that's a real killer. The thing is that when I get these boards done, I have to pay 100% upfront. So I pay for the bare PCBs, the PCB assembly, the packaging, the testing, the whole lot. I incur 100% of my costs before I have the boards in my hand and before I can start selling them. So it's a balancing act in terms of the economics of businesses like Freetronics and SuperHouse. It's a balancing act where I need to have enough stock on the shelf that I can fulfill orders, but not so much that I've got a whole bunch of money tied up in it. Now, if I had unlimited finances, I would just order big quantities of boards. Like I'd order 1,000 Ether 10s at a time and have, a shelf with boxes and boxes of stock. And then when I got down to say 100 left, I'd order another 1,000 to be produced. But the economics of it just don't allow that. So I normally have these boards produced in batches of 144 at a time. And the reason for that is it's just a packaging number. We have little we have storage boxes which contain 6 product boxes inside them, and then they go into a shipping container which has 6 of those boxes. So 6 sixes are 36. So for one layer in the shipping carton, we have 36 boards, and then we have 4 layers within that. So that is a total of 144 of the product boxes that go inside one shipping box, which is like 15 to 20 kilos, depending on the particular product that's inside it. So the result is that my production quantities tend to be multiples of 144. And so what I'll do is produce 144 of the Ether 10. It sits on the shelf. When the number gets down to probably about 15 left sitting on the shelf, I'll order another 144, and then it takes 6-7 weeks or so for production, and hopefully I haven't run out in the meantime. But I can't afford to just order thousands of them. So what this means is, to get back to this question of running, providing 2 versions, one with and one without this converter chip on it, it means that I've got an extra stock line that I have to maintain stock for and pay for batches to be produced. And despite the seemingly high prices that I charge for my boards, there really isn't margin in it. It's just an unfortunate thing that I'll stick to the technical stuff now. I won't get diverted into that too much. But like if you look at an Ether 10, I sell an Ether 10 which is like an Arduino Uno with Ethernet on it for $59 Australian, and I have many people look at those and say, "What? I can go out and buy a Raspberry Pi and like pay less." So, well, fine, you can buy a Raspberry Pi and pay less, but I can't sell them for less than that because I'm just losing money. So the economics of small-scale electronics production mean that my prices end up being significantly higher than typical clone boards that you get out of China, and I don't make much margin on them. So that's just the way it is. And James asked whether these Ether 10 changes that I'm discussing will be rolled into the Ether Mega, and I think I probably will. I've just had a suggestion to jump back to full screen mode. I don't know why, because it means you're looking at me instead of a schematic. Why? So, yes, my plan is, part of this is a matter of working through the various boards that I produce and converting them over to USB-C. So it's partly that, and partly replacing the WIZnet chip. So the Ether Mega uses the same W5100, which is now expensive and hard to get. And so my plan is I'm using the Ether 10. Well, in fact, I've got a, let me show you something. I can't remember if it's up here or if it's in the other room. I think I had to move this recently. I'm going to be back in just a jiffy, because I should have a board out here. I do indeed. this is a process that began quite some time ago. This is an EtherMega 2 or an EM2. You can see it's got USB-C on it. And what else did I do? This one, I can't even remember what processor this has on it. So, not the processor, it's still a 2560, but what is the Ethernet chip? Let's see, I can't remember. This is just to look at it. I think this one, yeah, this one has the WIZnet W5500. So, so this is an EtherMega with USB-C and a WIZnet W5500. And because it's a prototype, as you can tell, so I haven't even bothered fitting headers on here because I was just messing around with trying to get the Ethernet chip working properly and all those things, and there are even bodge wires on it, so we don't have proper focus. But there's just here, there is a little bodge wire, and there are some surface mount resistors soldered on their edge onto the edge of the WIZnet chip, which was a very tough job to do. So I started off with I started off with making some of these changes to the EtherMega, and I kind of got sidetracked and never got back to this project. In fact, I am really curious to know now. I want to know when I was doing that, because it was a while ago. And also, this was with the horrible USB-C connector that that includes all of the parts. So I've got to find the design. Is this the one? No, I've got to find the EM2 design. That one has had some more changes to it. EM2. Yes, I think this board is the one that is this one right here. So EtherMega 2. So it's EtherMega version 4 essentially. And this is the WIZnet W5500 chip on here. And USB-C. My computer is being super laggy. Just zooming is taking ages. So that's the horrible USB-C connector. And you can see here it's a combination of through-hole pins and surface mount pads, and most of them aren't even being used. It's only the power and the data, like the USB 2 power data pins, that I care about. But the reason for looking at this is I wanted to check the date. What is the date on this? 2018-04, so it's a bit over 2 years ago. So 2 years ago I produced these prototypes of the EtherMega version 2 with USB-C and the 5500, and that project stalled and fell over. Well, it didn't fall over, I just didn't get back to it. So what I decided to do was, instead of continuing with the EM2 design, I put that aside and I went back to doing the EtherUno instead. So my plan basically is to sort out the issues and get everything working with the EtherUno, with the new WIZnet chip, and now, having talked this through a bit more, by changing the USB to serial converter. And then once I've got this sorted, I will go back and revisit the EtherMega 2 and do the same thing. So, okay, so just checking. Alright, so there's a comment by Sion, Unexpected Maker. I would like to get back to this. So Sion said that we should have a discussion about the cost of manufacturing, and yeah, I think it would actually be worthwhile pursuing that conversation with Sion on the live stream with me, not just in chat. So I can talk about it from my perspective, but Xeon has also gone through a really interesting journey over the last couple of years with ramping up tiny Pico production and scaling that, and and I think having him directly on the live stream to tell his story would be worthwhile. So Xeon, I think the cost of production conversation is a really good one to have, but let's hold that. We won't have it on this particular live stream because it's just me talking. We'll do that some other time. Definitely worth coming back to. Now, the EtherUno. Alright, so we've got, we have the main processor and the USB to serial converter. Then moving on to the next part of the schematic. This is the power page. So we've got the 5 volt, we've got DC power coming in here and then a 5 volt regulator. This is a linear regulator. On the live stream last week we talked about linear regulators versus switch mode regulators. And this is also something that I have been debating with myself. I'm not quite sure what direction to go with this. My inclination at the moment is to leave this as the linear regulator rather than switching to a switch mode regulator. But I could be talked around. I'm not entirely fixed on that. This question has been going around and around in my head. I've been thinking about ripping out this voltage regulator and putting a switch mode regulator in its place. Maybe something like an EUP3476, the same as used on the Ether Mega. And what that would allow is for the whole board to run cooler. It could run off a wider range of input voltages. Like we could run, you could put 24 volts into it and it's not going to be too fast. If you push 24 volts into a linear regulator running something like an Uno, then it's going to have some problems. But there is a complication with that I will try to remember to get back to in a second. I've got multiple trains of thought running here. So there was a comment earlier about heat, and where was that in the chat? Oh yeah, so Station 240 said, does the W5500 on the Ether Mega 2 WizNet chip run hot too? No, sorry, I was going to mention that earlier when I was talking about all of the disadvantages of the WizNet W5100. One of the advantages of the newer chips, like the 5500 and the 6100, are that they run cooler. They are physically smaller chips, smaller silicon, fewer pins, and they take less power. So the whole board doesn't run as hot. And that in itself is a very good reason to be switching over. So one of the difference. Alright, so WizNet now have a range of different chips available. So there's the 5100 is the old one. Then there was a 5200. I think there's a 54, a 55. There's a 6100. And what they've done is, with their more recent versions, like the 5500 and the 6100, they've based them on the same silicon. Or substantially the same silicon. I don't actually know internally what they are doing, but what it looks like to me from the outside, just seeing what they do, I think what they've done is they've taken a standard processor core and their silicon is essentially a regular microcontroller with an Ethernet interface built into it, and what they are doing is running their own custom firmware on it, obviously, and they're being produced for them. So they're being, what I don't know is whether the silicon is being custom produced. I think it probably is at this point, even if it may not have been in the early days. Like the with the WizNet W5100, I suspect that the silicon for that was not really custom. It was probably like an off-the-shelf design, and they were kind of abusing or forcing it to do what they needed it to do, but it was not really very well optimized. And that's one of the reasons that it used a fair bit of power and ran very hot. Whereas now there is the 5500 and the 6100. those chips are all footprint compatible, so they're pin compatible. You can design a PCB for a WIZnet 50, I can't remember which part numbers, but I think it's the 5400, the 5500, the 6100, and the footprints are all identical. You can just drop a different chip down and they will all work. They do have some different modes, and the 6100, for example, which is the one that I'm currently specifying for the EtherUno, has more memory, which means that it can support, it means its packet buffers are bigger, it can support more simultaneous sockets. The original W5100 could only support 4 sockets simultaneously, and then with newer versions, they've increased to like 8 sockets that they could handle simultaneously, and the TX and RX buffers got bigger, and they got cooler and smaller and cheaper, so just better all around. And in the 6100, it also supports IPv6. So what this would mean is that you could be running IPv6 on an EtherUno, which is really interesting, and it's important for some people. So I think that's a really good capability. Because the different chips, like the 5500 compared to the 6100, behave a little differently, they have different capabilities, they are not 100% software compatible. They're not identical, because they have slightly different registers. Like the 5500, I think, doesn't support IPv6. So all of the registers in relation to IPv6 just don't exist, or they're not exposed. And so you have to make allowances for that in the driver code that talks to the chip. Now I'll do this again. Okay, so what you can do, and you'll see this in just a moment, in order to allow backward compatibility, there are mode pins on the modern WIZnet chips that allow them to switch into older backward compatible modes. And I actually think this is really clever. I like the way WIZnet is approaching this. What they now have is a family of chips which are pin compatible. You can just put a different part on the board and not change anything electrically, make minor changes to software, to your driver code, and then you get new capabilities. And these chips are being maintained and supported in parallel, so that for people who don't care about IPv6, you go for one of the cheaper chips that doesn't have IPv6 support. But if you do care about IPv6, you put on the WIZnet W6100 and you get IPv6 support, but you haven't had to change your footprints or do anything else, which is nice. I really like that. So I think their model strategy right now is really good. The 5100 was a bit of an ugly chip to work with, but the newer ones seem to be much better. And I do like that compatible family sort of approach. So we will look at that in just a second. But what that ties into is heat, and coming back to the power supply question. Now, one of the reasons that whole discussion came up last week about linear regulators versus switch mode power supplies is that someone on the Discord had designed an EUP3476 switch mode regulator chip into one of their projects, and because it wasn't using very much power, the voltage regulator was making weird noises, and it was running at a very low efficiency. And that's kind of what kicked off my my little commentary last week about linear versus switch mode supplies and optimal operating ranges. So a switch mode power supply is designed to provide power within a certain current range, and that's really where it's going to be efficient. If you take a switch mode power supply and you only pull a tiny amount of power out of it, like smaller than the way the circuit has been designed, it won't run very efficiently, and you can get audible sound coming out of the power supply, like you'll hear a little whistle or a whine or something, and that is because of mechanical stress that is being applied to the inductor, which is essentially just a coil. So you can think of an inductor as being like, it's almost like an electromagnet. It's a coil of wire, and if you are trying to drive that in a way that's not really optimal for the inductance of that part, the magnetic field around it will be trying to make the coil move. And so that's why power supplies can sing sometimes. You hear them like whistling at high frequency. And it's because there is actually physical stress being placed on the parts in the power supply, and they are trying to vibrate. So they're vibrating at a very high frequency, and you can just barely hear them. And when they are out of spec like that, so the switch mode power supply might be trying to provide a very small amount of power, it's not running efficiently. So you end up with power loss and bad things happen. So, so the question is, with the WIZnet W6100, it's a much more efficient chip than the old 5100, and you can tell that just because it doesn't get hot. But it also means that it draws less power, and that then decreases the overall power requirements of the board, which then puts it below the optimal power range of something like an EUP3476 switch mode regulator, and then it can begin to stress the regulator. So not pulling enough power is potentially a problem. And Stephen W. asked, is that what's generally called coil whine? Yeah, well, you could call it coil whine. So an inductor is a coil, and if you are making it oscillate, then it will physically move. So that's where the yeah. Oh, and Cam Brown said the singing is generally from discontinuous current mode. Under reasonable current, the inductor current is just a triangle wave with a high DC offset. Yeah. So yeah, exactly, that's right. So when you are not pulling enough power out of a switch mode regulator, it is really not operating the way it should be operating. They are designed to have a certain amount of power pulled out of them, and if you fall below that threshold, they don't like it, and they can't run in the mode that they like to run in. Anyway, getting back to this design, my debate right now, getting back to this design, my debate right now is what to do about this voltage regulator. So I have this linear regulator at the moment on the board. Now with the linear regulator, if you pull less power out of it, it's perfectly fine. It gets happier and happier the less power that you pull. So switching to the 6100, if I just leave this voltage regulator part of the circuit exactly as it is, then everything will be fine. But we don't get the benefits of the switch mode supply, which is more headroom, so we can run up to a higher input voltage and higher current. So with the switch mode regulator that's currently on the Ether Mega, you can pull a couple of amps out of it at 5 volts, and it's pretty happy. It's not going to really be too upset. So yeah, I'm not so sure about this. I just don't know if I should switch this over. I think what I'm going to do is produce a prototype of the EtherUno with the linear regulator on it. So it comes down to that old principle of only change one thing at a time. Don't try to change everything. I'm changing the WIZnet chip already, so that's a major reworking of the circuit. And what I will do is make a prototype with this footprint, and then I'm going to experiment. I'm going to use I've got the EUP3476 regulator on external modules. So what I can do is just wire one of those into it in place of this linear regulator, I can just put some patch wires onto the PCB and see what happens. And I'm going to measure the current draw. So at the moment, I don't actually know how much current is going to be consumed by this. All I know is that it's going to be less than the current Ether 10. Yeah. Alright, so there was a question from the Z about, is IPv6 really needed for home use? Well, that is an interesting question. Really needed? No. But useful or interesting? Yes. And this is an area that I haven't talked about at all on any of my videos, but I think it definitely deserves some coverage in the future. I'm not going to get into this right now, but this is a squirrel that I could chase for a very long time, so I'm going to try to avoid doing that. I was just going to say, but the very brief summary is, and if I do that, I'm going to talk for the next half hour about IPv4 versus IPv6. So I've got to try to resist that. Alright, I will try to do that under 30-second summary. IPv4 is Internet Protocol version 4, which has been around for a very long time and has some major limitations. IPv6 is a newer version of the Internet Working Protocol, which has some big advantages and is not very well supported in microcontrollers, but should be. So I think having a microcontroller board that is IPv6 capable will be useful because it will allow people to experiment with it and start to learn about some of its capabilities. At the moment, not very many people use IPv6 for home networking or for like DIY type projects because it's a bit of a mystery, it's unknown. But if you can buy a board off the shelf and plug it in, and there are some examples and you can do some IPv6 stuff, maybe more people will get into it. And I'm going to stop myself there, or I'm going to keep going about IPv6. So we still got the auto switch circuit in here, so if power is being applied on VIN, it will prioritize power from VIN into the regulator and then out to 5 volts. And if there is no power, then it will use on VIN, then it will use USB power pass through to the 5 volt rail. So we've also got a 3.3 volt power supply. Once again, it's just a little linear regulator. So 3.3 volts here is used as a supply to the WIZnet chip, and it's also available on the Arduino header for Shields or other projects. And there's some decoupling in here. So what we've got is, let's look at the bottom one first. So we've got the 3.3 volt rail, comes through an inductor and goes to 3.3 VA, and that is then used by parts of the circuit for Ethernet. And there's some decoupling on here. The WIZnet chip internally uses 1.2 volts and it relies on a 1.2 volt power supply for a couple of things. There's a 1.2 VA and a 1.2 VD supply, so analog and digital supplies, but it has its own internal 1.2 volt regulator, which is exposed on one of the pins as 1VTO, or 1.2 volts out. So what I'm doing here is taking the 1.2 volt out from the WIZnet chip, and then I'm feeding it through a couple of inductors, and then I've got some decoupling caps, and then the result of that is filtered 1.2 volt power rails that go into the 1V2A and 1V2D rails back into the chip. Now the reason that there are a series of 4 100 nanofarad capacitors here in parallel, and there's one up here, is that they can go directly at the chip close to those pins. So there are four 1.2 volt digital input power pins on the WISnet, on the 6100. So I've put four 100 nanofarad capacitors on there, and so that's why there's a different number of capacitors on each of these power rails. So if we go to the Ethernet chip itself, so we've got the W6100 on here, and you can see a few power rails up here. So we've got the 3.3 volts coming in. We've got the 3V3A, which is the decoupled power rail that we saw on the previous sheet. And here we've got 1.2 volts out, which comes from the regulator that's built into the chip. And then we've got 1V2A and 1V2D as power inputs. So we've got some activity LEDs over here, and mode. I'll get back to mode in just a second. That's something I mentioned earlier. Now there's one really weird little thing in here, RSet BG. Now this is kind of annoying from a design point of view, like from a board layout point of view anyway. It's just it's a quirk of the WISnet chips. So what happens is that the RSet BG is, so RSet is not reset, even though you might think that. It is regulator set, and this is for, I can't remember the exact explanation in the datasheet. I'd have to read it again. But basically this is a control pin that is used as part of the internal regulator of the voltage regulator in the processor. And what the datasheet says is that you have to put a 12.3 kilo ohm resistor between this pin and ground. And you might be, so what, basically this is like a current limiting resistor, and it has to be that precise value, like a 1% rated value. So what I've got here is a 12K 1% resistor in series with a 300 ohm 1% resistor, and that is because there is no single resistor value in like in a standard resistor range, which will be the 12.3 kilo ohm resistor that you need to go onto this reference pin. And you might look at this and say, what the hell is going on here? Why would you design a chip that requires a very precisely specified external resistor, which is not a standard value, and then has to be made up using two resistors in series in order to get what you need? Now, obviously I don't know the internal workings of the WISnet chip, but my best guess is that what they are doing here is using this as a current limiting, or it's part of the regulation system for the internal voltage regulator, and they can't put these resistors directly on the die of the IC because the power requirement on them is higher than what can be achieved with the silicon directly in the IC, with the process that they are using. So I don't know what current goes through this. It just, in the datasheet, it just says put this resistor externally. So that's kind of what you got to do. So in this case I've used 0603 resistors, which I think are 1/10 of a watt. I can't remember. But 1/10 of a watt may well be more than they can achieve with their with the specific process that they are using for manufacturing this chip. I don't know. That's just a best guess. I might be wildly wrong there. But this is kind of a cargo cult thing where you have to just take it as the datasheet says. It says put a 12.3 k ohm resistor between this pin and ground, so you got to do it. and that's the best way to do it. So these are the mode pins. I was mentioning earlier the difference between the different WISnet chips, like the 5500 versus the 6100. There is mod 0, 1, 2, and 3, and if you tie mod 1, 2, and 3 to ground, and then mod 0, here we go, WISnet mode selection is here. This is the mode operator, and by default what I've got is pulled this to ground through a 10k resistor, and then there is a cut track jumper which you can solder across, which pulls it up to 3.3 volts. And so by default all 4 of these mode pins are pulled to ground, and what that does is put the W6100 into its native mode, and it enables all of the options. So it turns on IPv6 support and does all of those things. It presents all its registers in its own native mode. If you solder across that jumper so that it pulls mode pin 0 high instead, on startup the W6100 will go into a backward compatibility mode, and it runs as if it is a W5500. So it turns off IPv6, its registers are run as if it's a 5500, which means that if you have a driver library that supports a W5500, you can use this chip as a direct drop-in replacement by pulling that pin high, and as far as your code is concerned, it's talking to a W5500. So you've got 100% backwards compatibility with the 5500. But what I've done here is I've defaulted it to 6100 mode, kind of because I think that's more interesting. Maybe people will shout at me for this, but yeah. I've got it defaulting to IPv6 enabled. But this will be a prototype. We can see how it goes. Now, there was an interesting comment in here. Oh, James. Looks like there was a $25 super chat from James for the Don't Forget About Me fund on beta testing the new Ether Mega board. Yes, I kind of have forgotten about it. 2 years this has been sitting in that box. But at least now things are underway with the Ether Uno. I will make some progress on this, get the WISnet 6100 sorted, and then I can revisit the Ether Mega. Now the good thing is that now I've switched over to using this different USB-C connector, I'm going to revise that. So all of the lessons that I will learn from doing this conversion from the Ether 10 to Ether Uno, like the new WISnet chip, etc., the USB-C interface, all of these lessons I will then roll into the Ether Mega and do a new version of the Ether Mega as well. So thank you, James, for that. Ooh, interesting. I like it. I like when there are comments from people that know what they're talking about. So Cam Brown said, BG for band gap. It uses an internal silicon band gap and presents that voltage over an external resistor to derive an internal current reference. In IC design, it's easy to make a precise voltage, very hard to make a precise current or precise resistance, but once you have a current reference, you can geometrically scale it. Fantastic. Thanks, Cam. That is really interesting to know. So that pin name, the RSET BG, the BG stands for band gap. I have learnt something today. So I don't really know anything about the internals of IC design. I've looked at lots of pretty pictures of silicon wafers and X-ray pictures of chips and pictures of decapped chips and things like that. But the design of silicon I've got zero experience with, and this is one of those areas where there are limitations and practices that come about from working in the field, but if you don't work in the field, you'll never learn them. So, as Cam says, easy to make a precise voltage, very hard to make a precise current or precise resistance. Yep, cool. And where were we? All right, so status display, there are just some LEDs that show activity, collision, whether it's in full duplex mode or simplex mode. There's a speed LED, so it tells you if you're in 10 megabit or 100 megabit mode. Link LED shows you got the link in place. MAC address ROM. So I didn't actually intend this, but this entire live stream has turned into a bit of a walkthrough of this EtherUno design. Hopefully that's okay with everybody. Bad luck if it's not, because it's kind of too late now. It's happening. So the MAC address ROM. Now on an Ethernet network, each device needs its own MAC address, which is a unique identifier for the device, and it's part of the way that the lower levels of the networking stack work. So at the high level we use IP addresses to signify different devices on the network, but at the lower level, where the negotiation happens in terms of devices passing frames of data across the Ethernet, they use MAC addresses. And so you need a unique MAC address for each device. So the kind of cheats or lazy way of doing that is that you specify it in your sketch or your program, and that is really painful. This is a whole subject, once again, I could spend a lot of time talking about, but if you have ever done an Ethernet project using something like an Arduino and an Ethernet shield, you've probably seen at the top of the sketch there will be a section where it sets a MAC address, and it'll be a series of hexadecimal number. Well, it's actually a single number, but it's typically represented as pairs of hexadecimal digits. And the classic example is dead beef, like DE colon AD colon etc. As the example MAC address. Now, if you compile your program for your Arduino and you use that example MAC address and you put it on your network, it'll work fine, because that made up MAC address is going to be unique, most likely. Then you have a second Ethernet board, like another Arduino, and you load your code onto that and you put it on your network, and weird things start happening. That is because you now have two devices on the network with the same MAC address. And that doesn't cause problems at the high level of the application, because you have devices with, well, how to explain this? All right, imagine that you had two devices on your network with the same IP address. They're both on 192.168.0.27, for example. The IP address is how the devices talk to each other and how the packets are routed over the network to get from one device to the next. So if you've got two devices on the network with the same IP address, how are they meant to talk to each other? I mean, conceptually, that's fairly easy to understand. It's like having multiple houses on the same street with the same number. I mean, how is the postie going to know where to deliver the package? It's going to go to the wrong place half the time. Now, so you can understand that problem in the context of IP addresses. At a lower level, the same problem happens with MAC addresses. You have to have unique MAC addresses on your network. Now, the problem scope is different to IP addresses, because IP addresses are typically routed within a network, and then they can be routed off the network using NAT, and there are all sorts of things like that. MAC addresses have to be unique within the scope of the lower level connection within your Ethernet network. I'm doing such a bad job of explaining this. Alright, so the summary is you need a unique MAC address for each device on your local network. If that MAC address is being set by hard coding it within the program that you run on your devices, That really sucks because it means that you need to change the program and recompile it for each device that you put on your network. And even worse than that, I think, is that you start having to keep track of them. So in the early days, when I was setting up my light switches, I was using, so my very first Ethernet-enabled light switches had a Freetronics 2010 and a Freetronics Ethernet shield in them. So each light switch was on the network. And I actually maintained a spreadsheet where I listed all of the MAC addresses that I'd assigned and what device it was assigned to. So if I had to recompile the code for a particular light switch, I would look up my spreadsheet and see I've used this MAC address, and so I'd change that in my code and then compile it and flash it onto the device. And it was a total pain. Like manually maintaining a list of MAC addresses and making sure they're unique just sucks. Shouldn't have to do it. The way that is done officially, so that all manufacturers' devices work together, is that there is a consortium that issues blocks of MAC addresses. And so the actual range of MAC addresses is very big, and a manufacturer will go to them and say, we need a block of MAC addresses because we need to make like 10 million network cards, and we need 10 million unique MAC addresses for them. And they will be assigned a block of numbers from that range. And so part of the issue is that if you just invent your own MAC addresses, I mean, the probability is infinitesimally small, but it is possible that if you just invent a MAC address and put it in your device and connect it to your network, some other device on your network might already have that MAC address. Not a probability that you have to care about because the probability is so small, but it's theoretically possible. So because of the centralized allocation of MAC address ranges, it means that you don't have a situation where one big manufacturer will produce devices and then ship them out, and then another big manufacturer will produce devices and ship them out, and they have overlapping ranges. It's coordinated. So the way to do this, the simplest way to do this, from my point of view anyway, is to buy a ROM with a MAC address already in it that you know is going to be unique. And that's what this part of the circuit is. This particular chip, the microchip, the MCP24AA025E48, such a memorable part number, is an I2C device. And the only reason that this part exists is that it contains a unique number. That's it. It's a little 6-pin chip, so it's in a SOT, what is it, a SOT 23.6 or whatever it is. It's a device that when you connect to it over I2C and you say, hey, tell me what your ID is, and it returns a MAC address. That MAC address is burned into the ROM at the factory. So the factory that produces these, so Microchip, have applied for a range of IP addresses. They've got their range assigned, they know it's unique, and they manufacture these parts and this little ROM. Each one that comes off of the production line, they burn a MAC address to it, and then they mark that off their list so they can never use it again. Then they get to the next chip, they burn the next MAC address, mark it off their list, it can never be used again. So when you buy a reel of these little MAC address ROMs, it is a reel of unique parts. Every part in that reel has a unique ID in it. And that is the only reason the part exists. It means that you can slap that part down on a PCB, and then your product can query that ROM and get a MAC address out of it at any time and know it's going to be, firstly, it's going to be unique, so no other device in the world should have that same MAC, and secondly, it should be consistent. Every time that device starts up, it's going to get the exact same ID. Now the good thing is that this means that you don't have to care about MAC addresses in your program anymore. So you can say goodbye to that little header at the start of your program where you say, MAC address is U0X blah. You don't care about that anymore. What you can do is have a single routine in your program that is very simple. It's just opens an I2C connection to the MAC address ROM, queries it, gets the ID back, and then returns the ID. And then your program can use this when it starts up to read its own ID. And that means that you can compile the exact same code and deploy it on a whole bunch of different Arduino devices, and they will all have their own unique MAC address when they start up on the network. So I think that is pretty cool. This is probably one of the nicer differences between the Ether 10 and other Arduino compatible Ethernet capable devices. So, and there's the micro SD card slot. Nothing particularly interesting there. The only thing interesting to mention, which some people may not be aware of, I've mentioned this on the live stream before, but it's kind of a funny fact, is that micro SD cards are just an SPI interface. It's essentially an internal high-speed serial interface that has been externalized into a chip, which is quite clever because it's leveraging all of the development of the SPI interface, and that is normally used, between parts on the same PCB, and it's just saying, well, this particular part is not on the PCB anymore. It's inside, it's inside a little piece of plastic, or it's a bigger one. It's easy to see. So an SD card is really just a flash memory chip with an SPI interface stuck inside a plastic enclosure with some contacts on it. So the pads in a micro SD card slot are just an SPI interface. Alright, so let's have a quick look at the PCB. I've been talking about this for nearly 2 hours and we haven't even looked at the PCB. So let's just do a quick rat's nest to get rid of all of those ground things I haven't routed yet. This is the current state of the EtherUno, and as you can see, it's not finished because there are air wires hanging around here. Lots and lots of air wires, but I'm getting there. This is the Wiznet W6100, and over here, this is the ATmega 328P. And as you can see, the Ethernet chip has more pins on it than the main processor. It's probably also faster with more memory and a whole lot more capable, but that's just the way it is. Up the top left here, you can see the ATmega 16U2, so that's the USB to serial converter chip. Over here we have the USB-C connector. Down here, where all the big, massive of polygons is, that is the linear voltage regulator. That's a dual footprint. There's both a SOT89 and a SOT223, I think it is, footprint on there, and oh no, sorry, that's on the 3.3 volt regulator. I've got dual footprint there. So that's a linear regulator. That looks like a D-pack, I think. On there, the 3.3 volt regulator, I probably should have mentioned that. So let's go back to Schematic. This is a kind of curious thing that might be confusing if you look at it and don't know what's going on. Over here we've got the 3.3 volt power supply, and we've got 5 volts coming in from the other regulator, and then we're feeding it into what looks like 2 voltage regulators, which they're both fixed 3.3 volt regulators. There's a ground reference here, and they both have an output, and the inputs are joined together, the ground references are joined together, and the outputs are joined together. So what the hell is going on there? That is just a very minor manufacturing optimization that allows us to deal with changing part supply. Now, I'm skeptical that this is actually useful. I think we've only ever used one footprint. I think we've only ever used the SOT89 footprint regulators in the entire time we've been producing this board. But what this means is that you do not fit both of these regulators, you only fit one of them. And it gives you options on the PCB to decide how to populate it. So in the bill of materials and the production instructions that come out of this board, there is a note in here that these two parts are interchangeable and only one of them should be populated. So that is here. And the two parts have the same specs. They do the same thing. It's just they are physically different footprints. So you can see here that we've got the two regulators, and in fact the regulators are sitting exactly on top of each other. That's why these pads look really weird. You can see this pad in here, this ground pad, and then there's a bigger ground pad over here. That's because, and then in here we've got a little pad and a little pad, and then a big pad and a big pad. Over here we've got the tabs for the thermal connection. And what this is, and I'll see if I can grab one and move it just to make it obvious. So this is one of the voltage regulators, and I'll move this out of the way, and you can see that there is the voltage regulator that I've got selected at the moment and I'm moving around, which has got one footprint. And then you can see the other voltage regulator, which is still in its original position, which has a bigger footprint. And it just so happens that if you take these two voltage regulators and you stick them over the top of each other, like that, then the pads overlap where they need to, and they don't short circuit, which is very nice. And on the PCB, this gets produced with a footprint that has these weird shaped pads, but you can put either regulator down and the circuit doesn't care. It won't know the difference. I have a vague recollection that that was done at the time because there was an issue relating to availability of the LD1117 at the time. Once again, this is 10 years ago nearly, and sometimes one of those regulators was easily available and sometimes the other was easily available, and we just made the board so that it could work with either. So what else is interesting on here? You can see down in the bottom right here, that's where the SD card interface is. And one of the other things that I've just done on this design is I've changed from HC49 US style crystals to these little 3.2 by 2.5 millimeter, I think they are, crystals with external, you can see the ballast capacitors there. And so what used to be in this location was a much bigger crystal. And in fact, if I switch over to, let me see, go to Fusion 360, I've got it open here. So this is the same design. This is the EtherUno, exactly what we've just been looking at in Eagle. This is just the model of it in Fusion 360. And if we come in down here, this is the 3.3 volt regulator with its dual footprint. One of the regulators is there, and I'll just make that invisible. Oh no, they're both there. So you can see there is the small footprint regulator sitting on there, and then the model actually had the bodies of the two regulators occupying the same space. So the larger one was taking up the space. So then if we make that one disappear, I'll hide that in Fusion 360, and you can see the dual footprint on here where either regulator can go in and it will work just fine. And then we've got the 5 volt regulator over here. You can see I don't have models in yet for the capacitors. There are a couple of big electrolytics that go in here for bulk power supply decoupling. What else? Oh yeah, there's A6 and A7. Now one of the slightly annoying things about the integration between Eagle and Fusion 360 is that you don't really have control over what layers end up coming through into the Fusion 360 model. So what you can see here is a whole lot of stuff, like it's got RN1 and here you can see C25. Don't even know why that's hanging out there on its own. These are the part designators. I don't normally include part designators on PCBs that I produce, so I exclude those from the manufacturing files, and I only include the silkscreen that I specifically design. And it results in a much cleaner looking board, and for most people it's better because it doesn't have information visible on the board that isn't of any use to them. And that's kind of a personal preference, but that's just the way I do it. But what happens when I take the design from Eagle and then sync it through to Fusion 360 is the designator layers come through. So down here, for example, you can see the extra pads for A6 and A7, so those extra 2 analog inputs, and you can see the designator A6 and A7 are under there as well, kind of messing things up and making it look ugly. And you can see RN1 and RN2, those, and R3 and C31, those won't be visible on the final PCB when it's produced. They just won't be there. Oh, look. And that is why looking at these things in a 3D version is useful. I shoved the fiducial marker up into the corner because when I was looking at this in Eagle, you can see the fiducial marker up in the top right corner here. I was moving things around and I thought, oh, I need to get that out of the way. It was, I don't know, it was down around here somewhere where it was getting in the way. And I just grabbed it and shoved it up into the corner because there was space there. And what I wasn't paying attention to, because I don't have the silkscreen turned on at the moment in that view, is that it sits right across the labels for the headers there. So I'm going to need to move that fiducial marker again before this goes to production. You can see the small surface mount crystals on here in place of, so this design in the current Ether 10, do I have one handy? I often have one within reach on the board, on the bench, but I don't right now. They have the big silver HC49 US style crystals, which you'd be familiar with. You've probably seen them on many, many boards, and I've replaced those. So you can see there's a big gap here up in the top right around the crystal, and you can see there's a fair bit of space here around this crystal, and that's because they did previously have much bigger crystals in those locations. And the ones that were on here previously were through hole as well, and this is part of a very minor assembly optimization, because if we can get away with using more surface mount parts and fewer through hole, that makes assembly easier in the factory. It means they can put this on with as part of the same pick and place process, and it gets reflowed with everything else. It doesn't have to be selectively soldered or wave soldered or whatever they end up doing in the factory. Now you can see here on the design that there is a big ICSP header here in the standard place where every Arduino has it. It's part of the R3 header spec now, so it has to be in that location. And that's the ICSP header for the main processor, which is down here, the ATmega 328. And then over here you can see another big ICSP header, and that is the ICSP header for this little chip up here in the corner. That's the ATmega 16U2, so that's doing the USB to serial conversion. So we've got the USB-C socket here connected through to the 16U2, and we've got the crystal for the 16U2 so that it can set its own clock frequency accurately, which is necessary for accurate serial communications. And down here is the polyfuse. So it's a 500 milliamp polyfuse to protect whatever computer you plug this into. Make sure it doesn't pull more power than it should. So if I end up swapping out the 16U2 for a dedicated USB to serial converter chip, like a CP2102N, this chip will be replaced. This ICSP header will go away. I wouldn't need this at all, so I'd gain some space there. Basically, yeah, it just, things get simpler and smaller and cheaper. So yeah, I'm really inclined now to switch that USB to serial converter. What else interesting is there? Oh, there's the PoE header. So this particular Ethernet mag jack has magnetics in it, which means it's got tiny little transformers inside the jack, and then it's also got some diodes. So so what it does is expose the PoE power on a couple of pins, and then we bring that through here, and the plus pin here and the negative pin here, these are connected through to the PoE lines, the PoE transformers, which are inside that connector. And then from this header we can either pass that power straight through into the power rail of this board, or you can put a module up on here and do power regulation, like if you want 803.2 AF power regulation, like 48 volts PoE, then you can be fully standards compliant by using an external module that just goes onto that header. And here you can see another hole, up here is a hole. Those are just mechanical mounts for the module that sits over the top of this whole thing and provides the PoE regulation. And now somehow I have gone from thinking I will quickly show you this before I get on to other things, to having talked about this for 2 hours. Where did that 2 hours just go? This is what happens when you stick me in front of Eagle and I just start talking. What else is interesting? Oh, up here. So this thing up here, the 3D model for this is not correct. This is just a block, but if I make that go away, there is a SOT23-6 footprint just there. That is for the MAC address ROM. So it sits up there. It's a fairly cheap and small part, and it's I2C, so it's easy to talk to. It's all good. I like that solution. Okay, so I'm going to wrap this up in a second, but I think my checklist for what still needs to be done to this board is I've got to finish routing around the WISNet 6100, and let's go back to the design in here. As you can see, there's a bit more routing to do here, and I'm resisting the urge to make this a 4-layer board so far. I think this is all perfectly routable as 2 layers, and in terms of EMI and other considerations, going to 4 layers would mean that I could have a dedicated ground layer and a dedicated power layer, and then 2 signal layers. At the moment what I've got is only a 2-layer board, double-sided, so it mixes ground and power and signal lines all together, but I don't think that's a huge problem. I don't think we have a really big EMI problem, and it routes fairly easily. So if I go to a 4-layer board, it adds a little bit of cost to manufacturing. I don't know, it's a trade-off. If this board was more complex, I would be inclined to go for, I'd switch it to a 4-layer board and have dedicated power and ground layers, but this board is kind of on the borderline. It doesn't really justify a 4-layer board, so I think I'll keep routing it as a 2-layer board, and I'll just see how it turns out. So I've just got to route a few of these tracks through here, nothing much more to do there. And the other major change, having talked this through now, is I think I'm going to rip this out and redo this whole USB to serial converter part of the board, which means that this, oops, don't want that, which means that this ICSP header is going to go away. It's just not relevant if I switch to a CP2102N. And this will be replaced by the CP2102N. I think a lot of the routing around here will get simpler. I think it'll just basically make life a little bit better by making that change. So I need to do that as well before I send this off to production. And I think that's about it. I apologize if I didn't get to important things in the chat. I've had my friend Andy watching the chat and feeding some things to me through a back channel, so that hopefully I didn't miss too much. But if you had questions in the chat, I'm sorry. Yeah. Okay. Oh. Sion said, keep it 2 layers if you can, and cost and troubleshooting at 4. Yeah. And as Peter Kirkos said, 1 less step during manufacture. No code to upload if I switch the USB to serial converter. I think there are enough benefits to switching, and losing the ability to do that HID emulation, I don't think it matters for the Ether 10. It's really such an odd use case for this specific board that I think it is fine. I need to standardize on the CP2102N for my various projects. So, to wrap up, just a reminder, I am going to be on that MakerCast live stream, so I will drop that URL back in here, and you can go and click on the little notify button so that you know when it's going to start. I've got to get up. What is happening with my video? I'm seeing weird things happening. Hopefully it's still working. I've got to get up very early in the morning tomorrow to jump on that live stream, and I've got to remember Patreon discount codes. I will generate a new code this afternoon and send out an email to all of my Patreon and GitHub sponsors supporters. So thank you very much. And remember, there's that design review channel now in Discord. So I will drop a Discord link in here as well. If you're not on Discord yet, it is the greatest thing ever. Well, I've been really enjoying having a Discord and chatting to people about projects. Yeah. Oh, a last minute comment from Mike O'Connor. Hey Mike, said, wish we could just drop the USB and go to OTA, which is over the air, using another small micro. Well, maybe an ESP32, maybe an ESP8266. That's a different type of board. Yeah, over the air. Yes. Well, I'm going to go and have some lunch and chase up those Patreon discount codes. So thank you very much for coming along to my little monologue today, looking at the progress of the EtherUno. Not quite what I expected to spend 2 hours talking about, but that's the way the cookie crumbles. So thank you very much for coming, and I will talk to you all really soon. And see you in Discord. Have a great weekend. Oh, yes, and as James says, happy 4th of July for US viewers. So, goodbye, everybody.